Hello everyone, welcome to my third lecture of signals and systems. So today we'll study about standard signals. So what are these standard signals? Standard signals are those signals which comes more often when we deal with real world input signals or output signals, or any random signal can be shown, can be expressed as a combination of these standard signals. Okay, so what are these standard signals? First of all, unit step or Heaviside step function. So unit step function is a function whose magnitude is 1 for time greater than 0 and 0 for time less than 0. Okay, and at t is equal to 0, the magnitude is half. For example, DC voltage applied to a circuit is called a unit step or Heaviside step function, and it looks like this. So step function which have a magnitude of 1 is called unit step, but naturally step functions can have many values, like it necessarily not need to be 1. Okay, and why this is called Heaviside step function? Okay, Heaviside is the name of the inventor. Okay, so Oliver Heaviside was a self-taught electrical engineer who used, this is the picture. Okay, so he invented the Heaviside step function or unit step function to calculate the current when an electric circuit is switched on. So what happens when an electric circuit is switched on? Before turning on this switch, the voltage applied to the circuit was 0, and after turning on the switch, the voltage applied to the circuit is the same as this applying voltage, maybe 5 volts, maybe 12 volts, okay, whatever. So it looks exactly like a step function, need not to be unit step, okay, because the value of the voltage is not 1 but 5 volts, but that's not the point. Okay, so next we will study about another standard signal, that is, okay, so before that let's simulate this output signal, that unit step Heaviside function, in MATLAB. Okay, so MATLAB is a simulation software where we input code or script to get some output for mathematical calculations. Okay, so here is the screenshot of the code I have written, stepresponse.m, and MATLAB files are generally saved as with .m extensions. Okay, so the code is simx. So what are this syntax? So simx is a syntax which creates a variable x with a positive rational value. Okay, and a plot is a syntax which plots over the specified interval. In this case, the specified interval is -2 to +2. So it specifies the interval as 2-element vector of the form x minimum space x maximum. Okay, in this case x minimum is -2 and x max is +2. Next, within the a plot syntax we have Heaviside first bracket x. Okay, so this is the unit step function. In MATLAB you can't write unit first bracket x, you have to write Heaviside to get the unit step function. Okay, and after saving and running that script, we'll get this output. So with the blue line we can see the magnitude. Okay, so at 0 time the switch didn't turn on, and before that the magnitude was 0, and after the t is equal to 0, as we can see from the blue line, the magnitude is 1. Okay. Next we will study unit impulse, or it is also called Dirac delta function, named after his inventor Paul Dirac. Okay, so unit impulse is a signal which has infinite magnitude at time equal to 0 only, and at other instance of time the value is 0. Okay, and it is represented mathematically with del third bracket n, and the value is 1 for n is equal to 0 and 0 for other values of n, and looks like this. So Paul Adrian Maurice Dirac was an English theoretical physicist who is regarded as one of the most significant physicists of the 20th century. Okay, and he invented this impulse function, so this function was named after him. So let's run the MATLAB code for showing the output of the unit step function. We'll generate unit step function in MATLAB. Okay, so for that, the file name, as you can see, is impulseresponse.m. You can give any file name, must not start with any number. Okay, so here in the script we can see the first line syntax is x equal to -1, then colon, then 0.1, then colon, then 1. What does that mean? Okay, that means variable x is defined as number between -1 and 1, that is +1, with interval of 0.1 between those numbers. For example, -1, -0.9, -0.8 up to 1. In line 2, we can see y equals to impulse function of x. In MATLAB we don't write impulse function, we write Dirac x to represent impulse function. So in MATLAB the syntax for impulse is Dirac x within first bracket. In line 3, here is idx is equal to y is equal to infinite. So idx is a variable which is equal to y equal to finite, is equal to infinite. Okay, in line 4 we have set y within first bracket idx is equal to 1. In line 5 we have stem within first bracket x comma y. So what does that mean? It is a plotting syntax. Previously we have used a plot, and now we are using stem. So plot values of y for discrete x values. Okay, a plot uses continuous values, but when we have to plot discrete x values we have to use stem. And within first bracket the first variable should be on the x axis, it not necessarily be x. In other case it can be t or whatever independent variable we have defined, like time is independent variable. Okay, and upon that the magnitude, in this case y, is dependent. So y is a function of x and x is independent. So stem plot is used in case of discrete functions. Okay, and here we get the MATLAB output for impulse function or Dirac delta function as you know it. So we can see here, so don't confuse the step function output with this impulse output. See the value for magnitude greater than 0, for time greater than 0, the magnitude is 0. But in the case of step function, the magnitude was 1. So this value is 1 only for t is equal to 0, and for other values it is 0. So it is 1 for t is equal to 0 and is equal to 0 for t not equal to 0, as we have defined before. So let's talk about elementary signals. So what are these elementary signals? Elementary signals, sinusoidal and exponential signals, are called elementary signals. Sinusoids and exponential signals are important in signal system analysis because they arise naturally in the solution of differential equations. So sinusoid, as we know it, like a sine omega t, where omega is 2 pi ft. So sinusoid signals can be expressed as a sine 2 pi f0 t, or it can be represented as 1 by t0. In this case, f0 is represented by 1 by t0. So the equation is a sine 2 pi by t0 into small t. So radian frequency form is omega 0 t. So omega 0 is the radian frequency form. The amplitude, the value, is represented with a unit of radian. Okay, radian per second. And if we take f0 frequency, then it is represented in hertz. Okay, like 50 hertz, 60 hertz, f0 equal to 50 hertz or 60 hertz. Okay, so t0 is the time period of the sinusoidal wave, like the time taken by the sinusoidal wave to complete one full cycle of the sinusoid, like going from 0 to maximum value, maximum positive value to 0, then 0 to negative maximum value, then negative maximum value to 0. That is one cycle, and the time taken to complete that one cycle is called time period. Here it is given as t0. So exponential signals. So exponential signals, as you can see here, x of t is equal to capital C e to the power at. Okay, so C is the amplitude of exponential signal, and C and A are in general complex number, so it can also be real values, like positive numbers, need not always be complex numbers. So it depends what value you are taking of C and A. It will change the form of the graph we will get. We will see next. Okay, so depending upon the values of C and A, it can exhibit several different characteristics. So let's see those characteristics. So before that, we have to know about Euler's formula. So what is Euler's formula? The Euler's formula is named after Leonhard Euler. It is a mathematical formula in complex analysis that establishes the fundamental relationship between trigonometric function, that is cos, sine, and the complex exponential function. Exponential means e to the power at. Okay, so Euler's formula states that for any real number x, e to the power ix is equal to cos x plus I sin x. It is also represented as cis x. Cis means cosine plus I sin. In short, it is called cis, CIS. So in this case, E is the base of natural logarithm, I is the imaginary unit, also sometimes represented by small j, and cos and sine are the trigonometric functions, cosine and sine respectively, with the argument x given in radians. This complex exponential function is sometimes, as we said before, denoted as Cs. The formula is still valid if x is complex number. So whatever the value of x is, the formula is always valid. So we can write like e to the power I 2 pi is equal to cos 2 pi plus I sin 2 pi. E to the power I 10 pi is equal to cos 10 pi plus I sin 10 pi. Okay. So let's study continuous time, complex exponential and sinusoidal signals. Okay. So the next signals we will study, all the signals are continuous time signals. Okay. So when C and A values are real, it is called real exponential signals, denoted as before. X of t is equal to c into e to the power at, and x and c and a values are real. So in this case we have taken c values, c is equal to 2 and a is equal to 6, and the real exponential signal is 2 into e to the power 6t, and it looks like this. So these are the two values for different values of a. Okay, so this is not 2 e to the power 6t, this is some random graph. Okay, and when a is greater than 0, a has a positive value, the exponential function grows with time, okay, with the value of t. So for e to the power 1t, 2t, 4t, the graph looks like the graph on the left side, and for negative values of a, the graph looks like graph on the right side. Okay, so if the value of a is imaginary in nature, the signal is called periodic complex exponential signal. So something like c e to the power j omega t, where a is equal to j omega. So for different values of f, so where is this f coming from? If you have w, which I have written to represent omega, actually omega is equal to 2 pi f. Okay, so omega is proportional to f. So for different values of f, we are seeing different images like outputs. So more the frequency is, the more the time period will be less. Okay, as you can see from the graph. So general complex exponential signal, if the value of a is complex, then what happens? So let's take a complex value, suppose r plus j omega. R is the omega, in this case w is the angular frequency, and r is something like 2, 3 real numbers. Okay, so x of t is equal to c into e to the power r plus j omega t. As we have seen before from the Euler's formula, we can represent e to the power r plus j omega t as cos omega t, r plus j omega t plus j sin omega t, like c into e to the power rt. Why we are separating rt? Because r is a value like 2 or 3, and when we take that value out of the equation, what we have left is e to the power j omega t, and e to the power j omega t can be represented as cos omega t plus j sin omega t. And the output graph you can see on the right side is the output of the signal. Now look here, there are two signals. On the above picture we have sinusoid whose amplitude is increasing exponentially. And on the below picture, on the bottom picture, we have a sinusoid whose amplitude is decreasing exponentially. So in both this picture there are two envelopes or exponential signal. On the top one we have exponential which is increasing, and on the bottom one we have exponential function which is decreasing. So let's talk about another type of signal, odd signal and even signal. So what is even signal? Even signal are those signals which are identical to time reverse counterpart, that is mirror image. It may be continuous or discrete. Okay, so it looks like this, like at t is equal to 0 we are holding some mirror and the mirror image is on the negative side of the function of the graph. Okay, so it looks like we are holding a mirror at t is equal to 0, and it may be continuous or discrete. And this even signal, it maintains a constant, that is whenever x of any function, whenever x of minus t is equal to x of t, it is called even signal. Suppose we are given a random mathematical signals, okay, and we want to determine whether it is even signal. So we have to put the value of t is equal to minus t and see if it equals to x of t or any other value. Depending upon that, we will say it is even signal or not. Okay, so on the left side we have continuous even signal, and on the right side we have discrete even signals. Now odd signal. Odd signal is not mirrored image but inverted mirror image. Okay, so it similarly it also can be continuous or discrete, and it obeys a function, a formula, that is x of minus t must be is equal to minus x of t for a function to be odd signal. So if you are given a random signal and you are asked to determine whether it is odd signal or not, you have to put the value of t is equal to minus t and see if it is equal to minus x of t or not. If it is, then it will be odd signal. If it is not, it will be not odd signal, not necessarily even signal, because for even signal it has to be plus x of t, but some cases for a given signal it might be neither of them. Okay, so odd signals looks like this. On the left side we have continuous odd signal, and on the right side we have discrete odd signal. So we can determine whether a signal, if a signal graph is given, we can easily determine whether it is even signal or odd signal, okay, from the picture. But if a function is given, we have to draw the signal, and in some cases it is not always possible, so we have to know the mathematical function to determine whether it is odd or even signal. Okay, so let's do an example problem. So the problem is, determine the even and odd part of the signal. So what are even and odd part of the signal? Like any signal in the universe can be represented as a summation of its odd part and its even counterpart. Okay, so to determine its odd part, what we will have to do? The formula for odd of x of t is equal to half of x of plus t minus x of minus t, and by putting these values we get 0 as the answer. So odd part of the signal, x of t is equal to t square is equal to 0, and even part of the signal, again the formula is half x of t, but in this case plus, not minus. Okay, everything remains same, just minus becomes plus, and we get t square as the answer. So of the function x of t is equal to t square is its even part and 0 is its odd part. Okay. So in this way, any signal can be broken into sum of odd or even. So it is. So that's it for today, guys. Thank you. See you next time.